Hello and welcome to this Immerse video series. My name is Adam, and in this video, I'm going to cover how to interpret and summarize mixture models with auxiliary variables. So this video is supported by an IES-funded training grant, and you can learn more about this project by visiting our website or following us on Twitter. And there'll be lots of other resources on our GitHub account. So here is a short description of what we're going to cover in this tutorial. And I recommend looking at these resources, these sources, if you're interested in learning more about M+ automation, the technical documentation for the 3-step, as well as other multi-step approaches that we're going to rely on to conduct this analysis. So all the materials associated with this tutorial can be found at our GitHub, on our GitHub page. And so these include all the materials for following along, including the data, scripts, and figures produced in this video. So if you want to practice, you can find those materials here and download them. We are going to continue on with this ongoing example from the Civil Rights Data Collection Repository. And there's some more information about this data set if interested. For this example, we're going to use LCA indicators measured for the state of Arizona in 2017, and our distal outcome variables are measured in 2018. So here we can take a quick look at our variables. These are 6 LCA indicators, which include 3 binary variables on whether the school reported students being harassed on the basis of disability, race, or sex, as well as 3 indicators on the number of staff, full-time equivalent staff, counselors, psychologists, and law enforcement officers, whether or not they're present at school. And here are our auxiliary variables. The first one, lunch program, will be covariate in our analyses. And this is a binary variable that indicates whether the school has a lunch program or not at the school. The next 2 variables, reading test and math test, we'll specify as outcome variables in our models. And this is the average reading test or the average math test assessment score at the school. So this video builds on previous videos in this video series. So if you haven't followed along already, there is a video on enumeration and the 3-step method. So these are steps that precede specifying auxiliary relations. So enumeration needs to be conducted first. And in this 3-step video, I go into greater detail into the syntax for conducting the 3-step method. In this video, I'm going to skip quickly through the syntax as I've covered it already in a previous video. And so just for context, here I'm showing the solution that was arrived upon in the enumeration step. So we conducted enumeration, and the 3-class model fit best. And you can see here the class sizes as well as the class indicator patterns. We can see in this green class, which represents about 11% of the sample, we have relatively high endorsement across the harassment variables, as well as the school staff variables. And in this pink class or red class, which is about 1/4 of the sample, we have lower endorsement across the three harassment variables and relatively higher endorsement across the school staff variables. And this blue class is the majority of the sample, approximately 65% of the sample, and has low endorsement across all indicators relative to the other two classes. So I'm going to switch over now to RStudio and get started with this these analyses. Let me scroll up here. So first I'm going to load in these packages. And we have packages for M+ automation for estimating the models, the tidyverse for manipulating data sets, as well as some packages for making tables and plotting. And next I'm going to read in the data. So you can see our data is in this data subfolder, and we're going to name it data 3-step. We're going to next conduct the manual 3-step. The reason we're doing this, as opposed to using the BCH approach, is that this solution has relatively low entropy or high classification error. So the BCH returned an inadmissible solution because of negative weights. And so that is the reason we're using that 3-step in this example. And here is the code for running the step 1 and step 2 models. And I'm just going to skip quickly through this. We have our auxiliary variables listed here. And in this next step, we're going to extract the logits and then use these to fix the parameters using the logit and this nominal n variable to fix the parameters in this step 2 model. And so I'm going to run this really quickly. And these models are generated here in this step 3 M+ folder. And so we can see our step 1 and step 2 models. We would want to, in a real research context, we would want to look closely to make sure that these models estimated correctly and that there's not too dramatic shifting of the class sizes or item probability parameters. And now we can go on to our first example of auxiliary variable relations, which is going to be just a simple distal outcome model. So in this model, we have our latent class nominal variable with 3 classes that's predicting reading test assessment and math test assessment. And so we can go on to specify this model. We're again fixing our parameters with the 3-step, but the new syntax here is in this model statement. Under the overall statement, we're just going to list our distal outcome variances, so estimate those variances. And then under each class-specific statement, we're going to freely estimate the distal outcome intercept means for reading test and math test assessment, as well as the variances. So the means and variances are going to be conditional on latent class, and we're going to label these so that we can estimate pairwise mean differences. So this is just repeated here under class 2 and the class 3 statements. In the model constraint, we're creating some new and additional parameters, which we've named here. We have our reading test pairwise differences and our math test pairwise differences. So we have all possible pairwise differences listed here. For example, for reading test, this is the mean for class 1 compared to class 2. And under model test, we're also going to conduct a wald test or omnibus test to see if at least one of these pairwise differences is different. But we can only conduct one wald test per output or per estimated model. So to work around this, you can comment out this syntax and uncomment this, and then you could run a model by a different model and change the name so it doesn't overwrite your previous model. And that way you can get a wald test for both the reading and math test assessment outcomes. So I'm going to just go ahead and run this model, which we've named example 1 distal model. So we can take a look here at this model output. And I'm just scrolling down here to the model output. So the model estimated normally, and we can see here the main focus of these results in a distal model will be these distal intercept means. And we can see that these are freely estimated by class. They're different in each class. And we can see the magnitude looks smaller for class 1 compared to class 2. And class 3 has the highest average reading test and math test assessments. So now we would want to determine whether these differences, these mean differences, are significant or not. And we can see this here for the reading test assessment and the math test assessment. In this case, all pairwise differences are significant. And so next, another way to possibly to present these results is either in a table or in a plot. So I'm going to show how to create a plot using R and M+ automation to plot these distal outcome mean differences. And so what we're going to do is read in this example 1 distal model output file and then extract the relevant parameters. So we can see here, we call this data frame model step 3. We can see we have all the parameters here, but we just need some of these to create the distal plot. So we're going to manipulate this data frame a bit. And here we're just going to filter out these means with these names, just filter those rows. And then here we're just changing some of the labels so that it makes a cleaner looking plot that is easier to read. So we can see here what we've produced. And we have all the information we need to create our distal mean plot. So using ggplot, we're going to create this plot. And here we can see that for this pink or red class, which is characterized by low reported harassment and high on the staff indicators, we have the lowest average reading and test assessment values in those schools, and then moderately higher assessment values for this green class, and much higher values for the blue class, which is almost twice as high as the values for the pink or red class. So this is a potentially interesting result. You could also add information about significant pairwise differences, but I haven't done that yet in this plot, but it would be pretty easy to add those in. So for our next example, we're going to specify a distal outcome model with a covariate control. So here we can take a look at this model. In this path diagram, we can see that the covariate lunch program predicts the latent variable harassment and staff like mixture model, nominal classes, and then the latent classes predict reading test and math test assessment. We also have the direct or main effect of X predicting both distal outcomes, and it is common as for like depending on your research question that you would include these relations, or you might get bias estimates. So we can continue on to specifying this model. In this model, we have here, I'm skipping down to the model statement. We have here we have estimating the covariate as a predictor of latent class. So that's that regression line of X on C. And then we have we're estimating the direct effect of Y on X in this overall statement. So these will be held constant across class. And we're also going to just list these variances for the distal outcomes. Under each class-specific statement, again, this is going to be the same as the previous example. We have listed our intercept and variance terms, and these are repeated under each class-specific statement. So the model constraint and model test will be the same. And in this example, I will estimate the wald test for math test assessment. I realized I forgot to look over the wald test results in the previous example, so I will take a look at that in this example. I'm going to run this model really quickly. And this model we named EX2 distal cove model. So we can see here our model output. And I'm going to scroll up to the wald test. If I can find it. Here we have the wald test. And we can see that for the math test assessment, there are, since this p-value is non-significant, it indicates that there are no significant pairwise mean differences in this model. And so that's an interesting result, which contrasts from the previous example. And scrolling down here to the model results, we see that these regression of X on Y for reading test and math test, and these are held constant, the same across class. And we also have our intercepts here, which after controlling for the covariate, we can see now are much closer in magnitude for class 1, class 2, as well as class 3. So we again can create a distal outcome plot showing those mean differences. In this case, there are no significant mean differences. Oh, I think I forgot to show that here. We can see that all the pairwise mean differences are non-significant, indicated here. And so now, since we've already gone over this syntax for creating these plots, I'm going to just look at them in the markdown. It'll look a little bit nicer. For example, 2, scrolling down. So here's the syntax. We can note that one thing has changed when you add covariates in the model. The labels for these intercepts or means changes from in the previous plot syntax. This was means and now it's intercepts. So you need to look within this model step 3 data object and see how those parameters are labeled so that you can extract the correct values. And here we're just calling this the same name, so it's going to overwrite from the previous example. And again, use ggplot to create this plot. And here we can see that those distal means are fairly close and the standard errors are overlapping, which indicates that those pairwise differences are non-significant. So here, in our third example, we're going to conduct a moderation model. And here we can see that we have our covariate lunch program regressed as a predictor of reading test and math test assessments. We have these main effects, and then they're going to be moderated by our latent class variable. And this is specified by simply putting the y on x regression under each of the class specific statements and estimating those conditional slopes. The slopes will be different based on class or freely estimated. So returning to RStudio, I'm going to skip down here, and here is our syntax for specifying this moderation model. And we can see first here that we're going to center our covariate. This is considered recommended practice often in moderation, so that our distal intercepts are held at the average of lunch program, at the grand mean of lunch program, as opposed to a different reference class, which would be indicated by 0. And under the model statement, we see we have our outcomes, our covariate, and our moderator, C. And in the overall statement, we have these, which are, I think the syntax is redundant. I think the model would run without these, because we also have these specified, these regression slopes and variances specified in our class specific statements. So here for class 1, we're going to estimate our mean intercept again, our variance, and then this slope coefficient of reading test on lunch program. And we're going to do the same for math test and repeat this syntax under each class specific statement. For each of these slope coefficients, we've also labeled these because so that we can estimate the pairwise slope differences and use these to evaluate our results to see if there is in fact a moderation effect or the slopes are different between classes. So in the model constraint, we've named our distal pairwise distal mean differences as well as our slope differences. So we have additionally these slope differences, pairwise differences estimated here. And in the model test, now there are 4 omnibus tests that we would be interested in. And so in a real research context, we would need to create multiple runs of this file to estimate each weld test and get the values for those weld tests. And so I'm just going to quickly run this model. And additionally, to create this simple slopes plot, we're going to need a model with the covariate uncentered. This allows us to get the estimates when our covariate lunch program is at the reference category or 0, and use those to create those simple slopes plots. We need those 4, or in this case 6 points for each class by lunch program is 0, and when for each class when lunch program is 1. So we can do this using this update function from M+automation, which allows us to take the previous model, and this is the previous model's input syntax, and we're just going to update this define section of the input syntax and just remove the centering argument. And then we'll just rerun this model and call it example 3 uncentered. So that's a convenient way to update and create new models in an iterative fashion. So I'm just going to run this, and we have our uncentered model here. And now I'm going to skip back to the markdown to take a look at these plot results. Scrolling down to example 3. So here we have our plot syntax, and here for our distal outcome plot. I'm not going to go over this in detail because we've already used this same syntax to create distal plots for the previous 2 examples. So we can just see the output results here, and you can see these A and B indexes refer to which means are significantly different. So this pink class, the mean is significantly different than the green and blue classes, but the green and blue classes are not significantly different, pairwise differences. And so yeah, this result has changed from the previous example with the moderation specified. And now we can create these simple slope plots to present the slope differences across class. And we're going to read in that uncentered model and then extract these relevant parameters. So we're going to need the slope parameters and intercepts, and we're just doing a little bit of manipulating the labels that will show up in the plot. And also, to prepare this data, we need to convert it from long format to wide format, and we'll create a simple slope plot for both for the reading outcome and the math outcome, and then we'll put those plots together. And so here we have our reading simple slopes plot produced. We're going to use this similar syntax to create the data frame for this math outcome simple slopes plot, and then create a plot here. And then we're going to combine the two plots using this patchwork package, where we're going to have the reading plot on top of the math plot. So that's done here with this syntax. And we can see here our simple slopes plot nicely. And we can see an potentially interesting result is that for this pink or red class, schools that do not have a lunch program are performing really low on these reading and math test assessments. So this is something we might want to look into further to understand why these schools are performing so much lower than the schools in these blue and green classes. Also, it's interesting that for schools with a lunch program, they're all performing clustered around this 40 mark for both reading and math test assessments. So it's really these schools without a lunch program that probably range in SES. So these, I would guess, are schools that are higher SES schools that are performing well without a lunch program because it's not needed. And then these are schools which may not have the resources needed or infrastructure for a lunch program. And these schools are performing much lower. So thank you for your time, and follow along for future videos. This video relies heavily on the M+ automation package, M+, as well as other packages. Please reference these sources. Thank you.